So the last thing that I'll summarize here, or a couple more slides to summarize, I know this is going a little long. If we look at now the trend of polar molecules on their boiling point and the trend of small polar molecules on the boiling point, okay? Water is a huge exception. And in fact, so is HF and NH3. So before we describe the exceptions, let's just look at the normal pattern. Let's look at methane. Non-polar molecule, right? There it is, carbon. So what we're going to do is start at all the various groups. So you notice group 2, 3, 4, and 5. So groups 2, carbon, silicon 3, germanium 4, tin 5. And look, you notice that there's a nice increasing trend as we increase the number of electrons and protons in that central atom. Look, CH4, SiH4, GeH4, SnH4. Boiling point increases as we would expect. But now if we go to the next series, so we just did carbon, silicon, germanium, tin. Now let's go to the next series. Nitrogen, phosphorus, arsenic, and, oh my God, I've totally blanked out, shamefully. I'll think of it. Antimony. Yes, antimony. So notice now NH3 is a huge exception, right? And the reason for that is because nitrogen, so we know that it has this structure, but so will these other molecules, right? pH3 will have the same Lewis structure. ASH3 will have the same structure. SbH3 will have the same structure. So why is NH3 now such a huge exception? It's because of the size. NH3 is sufficiently small. It's very small. And what that means is it can pack together with other NH3s quite well. And so the same thing is observed with HF, and the same thing is observed with H2O. So these are all very small. All of these, H2O, HF, NH3, and that makes them incredibly polar. And also, maybe you've thought of the other thing, hydrogen bonding, right? Hydrogen bonding is only observed between oxygen, fluorine, and nitrogen. So not only are they very small, they can pack together very well, but they're capable of hydrogen bonding with themselves. So that makes them exceptions for this trend in boiling point. And as you notice right here, if we look at like HCl and HBr, you know, there's a little bit of an exception, like a minor exception right there. But for the most part, like HCl, HBr, HI, they all follow the trend. H2S, H2SE, H2TE, it follows the trend. But because of size and hydrogen bonding, H2O, HF, and H3 are exceptions with this boiling point trend. Okay? So summarizing this, so this was a big lecture. So summarizing all this stuff, as far as relative strength, ion dipole is definitely the strongest. Okay? So like when a water molecule, for example, is interacting with an ion, that's quite strong. Okay? And I didn't really talk about these phenomenon that's in this chart, but I'll talk about that as we go. Hydrogen bonding. So I just want to use this chart to talk about order of strength. Okay? Hydrogen bonding is the second strongest. And in the absence of any ions, hydrogen bonding will be the strongest, right? If you're talking about systems where there are no free ions, hydrogen bonding is usually the strongest. Okay? However, of course, if we have ion-dipole interaction, that wins out. So the dipole-dipole is third. Okay? And so we talked about that when we compared the dipole moment, or the boiling point of acetone to that 2-methylbutane, I think the molecule was. So the dipole-dipole interaction is very strong. Dipole-induced dipole is in fourth place, and then in fifth place is the dispersion force. Now, what's interesting though about this dispersion force, I'm going to show you some examples later on. The dispersion force can actually become incredibly strong when the molecules are quite large. For example, I showed you that octane, which is nonpolar, it can only do dispersion forces. It has a boiling point of 126 degrees. Water only has a boiling point of 100 degrees. So we have to take these, this relative order of strength, we have to take it with a grain of salt, pun intended, because we know that there are these competing effects like shape, mass, hydrogen bonding, etc. So in general, this order holds through most things, although of course we know that chemistry is the science of exceptions. So a general understanding of this is sufficient.